Welcome to the lesson on transient solute diffusion in solid state. This is part of mass transfer, which is taken as part of the NPTEL MOOC on transport phenomena in materials. The governing equation that we are solving is basically Fick's second law for solute diffusion, and for this lesson we will restrict this equation to be for solid state, which means that we will neglect the advection term, and then we say that there is no reaction happening, so we neglect the source term, and we restrict the diffusion to be in one dimension, so there is only one term for the diffusion term, and we also say that there is only one single species that is taking part in the mass transfer. So therefore there is only one equation, and which looks like this: dou c by dou t is equal to d into dou square c by dou x square. This is also called as the heat equation because it looks identical to the transient heat equation from the Fourier conduction. Now the solutions for this equation depend on the initial and boundary conditions. So in this lesson we will take three situations which give us solutions that are widely applicable in the metallurgical domain. So the very first set of solutions we are looking at come under the category called error function solutions. So the problem definition that is suitable to make the error function solution applicable for our governing equation is as follows. So the examples that are in metallurgy, such as carburizing or nitriding of steels, are good examples for the error function solution to be applicable. The reason is that the surface composition is reached very quickly because of the interface equilibrium, and the composition at the surface remains fairly constant during the time when the process of carburizing or nitriding is taking place, and the solute, namely the carbon or nitrogen, would be diffusing into the steel. So we are actually interested in the early stage of diffusion process, and that means that as soon as the surface composition has reached a fixed value and stays there, and that's the process we are looking at. If you were to look at a very long term diffusion, then you may actually have flattened composition profiles which are not of our interest in this particular case. So the description of the problem is complete only when we have a schematic diagram. So this is the domain, and we draw it a bit longish because we say it's one dimensional domain, and on the left hand side is the boundary that is exposed to the surroundings, which means that's where the carburizing or nitriding is happening. The flux is actually coming into the domain from that side, and on the other side the boundary is far inside the sample, which means that it's a very thick steel sample, and the domain size is several times the diffusion length, which means that we can assume it to be semi-infinite domain, so which is very important for this solution to be applicable. So what we can imagine as possible composition profile is going to look like that. So this composition here is going to come from the equilibrium at the interface, and deep inside, of course, the composition is quite flat because it may not have as much carbon as on the surface. So these two values actually determine the problem definition. Okay, so we may call this value as the C infinity, and we may call this as the C surface or C naught, depending upon the notation that one prefers to have, and this is the distance. Okay, so now the problem is defined, so we will write down the boundary conditions so that we can have the derivation of this particular solution coming up to us. So on the left side we say that the composition at x is equal to 0 is C naught, and that's going to be fixed, and it has a finite gradient at that particular location, which means that the flux is actually coming into the sample. And on the right hand side we say that the composition is also fixed at a low value C infinity, and it has zero gradient. You could also see that the profile that we have drawn should also indicate the same, because here there is a zero gradient, and here there is a flux that is coming in, and both the values are fixed. Okay, so if these values are actually evolving, then that is not suitable for us. We must have them fixed at least during the short amount of time when this particular error function solution needs to be applied. And we say that's why that the time duration under consideration is such that the diffusion length is very small compared to the domain size. It's in the very early stages of the diffusion process. And the error function solution is going to be available to us through a technique for solving the differential equation, which is called the variable substitution. So like we have done in the heat transfer problems, here also we would actually create a new variable called eta and choose its functional form to be of the nature as given here, x by 2 root dt. So why is the 2 there is something that will be with hindsight, namely after we derive, then we come back and modify it so that the derivation looks elegant. So we write this eta, and then we want to actually convert the differential equation which has the differentiation with respect to the x and t. So we want to convert that with respect to differentiation with eta. So we first write down what is dou eta by dou t, and that is basically differentiating only with the time. So x remains constant there for this process, and then from there we can say that by expanding the dou c by dou t as dou c by dou eta into dou eta by dou time, then whatever we have derived here would go into this term there, so that we can express dou c by dou t as a differentiation with respect to eta, and there is nothing else other than eta that should be there in the term. So we have got the left hand side of our governing equation having obtained. And for the right hand side we has the same process. So we start off with the eta, and we have to then first determine what is dou eta by dou x. So that comes out to be quite simple, 1 by 2 root dt, and then that means that dou c by dou x can be written as dou c by dou eta into dou eta by dou x, and therefore we would write dou c by dou x as dou c by dou eta into 1 by 2 root dt, which means that when we want to differentiate a second time, then this factor is going to come 2 times. So which means that dou square c by dou x square is nothing but dou square c by dou eta square into 1 by 4 dt. So we now have the right hand side of our differential equation also ready. So we can then write the differential equation which we had earlier, dou c by dou t is equal to d dou square c by dou x square. In that we substitute for the left hand side what we have derived just now, and so that thing has to be brought in there, and for the right hand side also we have now derived the terms, so that would be brought in on the right hand side. So then we will see that quite straightforward, minus eta by 2t dou c by dou eta is equal to d into dou square c by dou eta square into 1 by 4 dt. So here you see that you could cancel out the t's, and you have got 2 going off and you have a 2 there, and so that d also will get cancelled out. So this 2 we will take it to the other side, so that we can express the equation in a simpler form. Now we also make one more change, dou c by dou eta we write as c dot, and dou square c by dou eta square we write as c double dot, so that the equation that we want to solve is quite simple. So c double dot by c dot is equal to minus 2 eta. So there comes the elegance of having chosen the eta to be a particular functional form. And we can now integrate this as follows. So we first integrate with eta. So we now have the differentiation of the denominator coming in the numerator. So the integration will give you the logarithm of the denominator. So that's what you write. Logarithm of c dot is equal to, then we integrate the right hand side with respect to eta, that's minus eta square. And of course you can have a constant there which is absorbed in the expansion. So you can write c dot is equal to a1 e raised to the power of minus eta square, where a1 is basically an integration constant. And when we integrate a second time, we cannot actually reduce it. So we integrate with respect to eta from 0 to eta, and we leave this expression as it is because we are unable to reduce it further. And we will then see that it is actually available as a tabulated function going by the name error function. So that's what we then refer. to here and we write it in a simpler form. The C0 and C infinity are coming from the boundary conditions because of the properties of the error function. So as we will see shortly, the properties of error function, that f of 0 is 0. So then you could actually see how this particular way you have written. So the properties of error function are as follows. So f of eta is given as 2 by root pi integral 0 to eta e raised to the power of minus eta square d eta, which means that there is a factor that is coming in here. Why is that so is evident when we look at the values of error function. When we differentiate, it should come to the integrand, so that's what it is here. Okay, and very often students make a mistake that when they want to differentiate error function with respect to x, they forget that this expression is with respect to eta. So if you wanted let us say dou by dou x of f, then you would actually write as 2 by root pi e raised to the power of minus eta square, and of course you have to write dou eta by dou x, and this fellow will turn out to be 1 by 2 root dt. So this factor 1 by 2 root dt will be missed out because sometimes this and this is confusing. Okay, so we have to pay attention to that. And how is the variation of this function looking like? So it goes from 0, the argument eta goes from 0 to a large number on the right hand side. So it goes up and then flattens out. And it is a odd function because when the argument changes the sign, the value of the function also changes. So f of 0 is 0, f of infinity is equal to 1, and f of minus eta is minus of f of eta. So it is this that requires the factor 2 by root pi. So this is because of this. So we wanted to have it scaled so that the definition of the function is elegant, and that's the reason why the scaling factor comes. Now we can also define what is called as a complementary error function as follows. That is RFC, that is the complementary error function, is defined as 1 minus erf of eta. Okay, so that is basically to flip the error function about the x-axis so that it will give a variation that quite suitably will fit for the problems such as carburizing or nitriding. So error function, complementary error function, is defined as 1 minus erf of eta. And naturally then you can also differentiate to show that it is nothing but minus 2 by root pi e raised to the power of minus eta square. So except for the minus sign, there is no difference with respect to the differentiation. And as I mentioned, it's flipped, and of course it is also moved up by a unit 1 here because you see there is a 1 here, and therefore you can see that erf of infinity is 1, so RFC of infinity will then come out to be 0, and erf of 0 should be 1 because this is 0 and therefore it will be 1. Okay, so this is how the complementary error function has been defined, and you could already see that the error function itself would go something like that. Okay, and it goes down to the other side. Okay, so it's flipped along the x-axis. So there is an application for the error function solution, and this we have to follow only when the conditions are suitable. Namely, at one end of the domain, the composition is fixed thanks to phase equilibrium or reaction equilibrium, and then there is a gradient that is present, and the gradient alone changes with time but not the composition. And the other end of the domain, the composition is fixed and the flux is 0. So this is the kind of scenario where you are supposed to use error function, and we can actually shift the scale of the compositions up and down, and also multiply with a factor, so that finally we can actually use the error function as it is, so that we can use the value of error function of infinity is equal to 1 in our problem definition. So this is what we do. So normally we scale the composition profiles in such a way that it should look like either error function or complementary error function. One of them should be possible for us. So the choice of C0 and C infinity will be given in such a way that it be okay. So if it is, let us say, error function, okay, so then you can already imagine that error function of is 0, which means c is c infinity at eta is 0, and f of infinity is 1, which means that c is c naught at eta is infinity. So you have to choose the symbols c naught and c infinity suitably, looking at what is the function on the right hand side. So sometimes we have a profile like that, and sometimes we have a profile like that. So we can choose accordingly the function that is applicable. Now, as the argument is changed with respect to only one of the two variables, x or t, only one of them, and how does the error function evolve? So you could see that as a function of distance, if you keep changing the time and increase the time, then it would appear like this. So with increasing time, you can see that the error function is behaving quite logically, as we would expect for the solute profile, because as the solute keeps coming into the domain, then you would expect that at any position the compositions should go up, and that's what is actually shown also by the error function profile. Okay, and we can use this to determine what is the case depth in the case of carburizing of steels, where we define a particular value which we want to say as the cutoff for the particular hardness, and then we can ask for a certain amount of time what would be the thickness that has been hardened. So these kind of problems can be solved readily because error function is tabulated and readily available. We just need to only know the diffusivity as one of the parameters that goes into this solution. Now there are some numerical approximations that are available for error function, which would make the computation easier. Sometimes if you do not have access to the error function or complementary error function, then you can use these approximations. So one approximation which uses e raised to the power of minus eta square, where eta is the argument, it looks like this, and you can notice that this is quite reasonable only at values of the argument above a particular threshold. So only for large values of eta you can use this particular approximation, which is just exponents, and for small values of eta you should not be using it because there is a large error that would come for small values of Fc. So this is an approximation for error function, complementary error function, which means that once you have the value, you can also evaluate what would be the error function itself. So now there's another approximation which is available for small values of eta, which is for the error function here. For the error function here, you could see that it is valid for eta less than 1.6, which is quite convenient here because you now have two approximations, one for the low value of eta and another for the high value of eta. So without having to look up the error function, using these simpler functions, you can actually evaluate the value of error function and use for numerical problems. There are many approximations that are available in the handbooks, so you could look them up if you are interested. Now there is a second class of solutions for the diffusion equation, which we call as the decaying exponential function. Now this is usually the very first problem for transient diffusions that are solved in many of the textbooks. I chose that to be the second case because we actually can reuse one of the solutions of the first case, and therefore we don't have to throw the solution from out of the blue. So the diffusion problem for which this particular solution is suitable is as follows. Assume that there is a thin layer of solute coated on the surface of a metal, and the solute is then diffusing into the metal because it is held at high temperature. So what happens is that the surface composition keeps decaying with time as the solute is diffusing into the metal. And very important condition that we have is the total solute content in the domain is conserved. Now this is very important because this is not really like a traditional boundary condition. So normally for a traditional boundary condition you have a value that is specified at the boundaries or a flux that is specified. But in this case the condition that is specified is that the integration of the entire solute profile in the domain is going to give you a fixed value at all times. Now that is the reason why this solution is a bit different for us to evaluate. The imagination of the domain is as follows. You have the long domain, which is semi-infinite, and on the left hand side is where there is a solute that is deposited as a film, so that's in green color. And on the right hand side the boundary is quite far enough, so we could assume it to be a semi-infinite domain. And we assume that the profile would look somewhat like this, drooping down and flattening out at the end. And the composition of the solute layer that is deposited is C star, and the thickness is delta by 2. Why do we choose as delta by 2? Because we want to imagine that this is one half of a problem, the other half is a mirror having a symmetry at this particular plane, so that we can actually use the solution that is available for the integration from -infinity to +infinity. Some symmetric solution can be taken up. The cross-sectional area of the domain is A. So which means that your boundary condition is going to be written as follows. From -infinity to +infinity, the integration of the composition profile is going to give you C star into delta, and A is a cross-sectional area. So now this is a very different kind of a boundary condition. And the other condition is that at x is equal to infinity, the composition is C infinity. And we also want to make an assumption that we want the solution only for finite time. We are not interested at t is equal to 0, because at t is equal to 0 there is a step function for the composition profile. We are not going to look at that. For finite time we assume that the composition profiles are smooth. So the proposed method of solution is see if the error function actually could help us. So in the error function solution we do have an integration that goes from -infinity to +infinity, or from 0 to infinity, which is basically the value of error function at the argument value going to infinity. So can we use that for our solution? So let us look at the error function, and we see that when we differentiate, the function should look like this: 2 by root pi e raised to the power of minus eta square, and eta itself is 1 by 2 root dt. So we just substitute that, and because we know that error function at infinity is 1, so we can try and plug in this, and here we see that what we have done is nothing but this is plugged in here, and then we have a scaling factor C star and delta as required by the boundary condition. So we basically what we do now is plug in this expression of the C, plug in this expression for C, which is basically of the form 1 by root t e raised to the power of minus x square by 4 dt, and then we plug it into the diffusion equation and check. And if you can do that algebra, which is not very painful actually, then you would see that this functional form actually fits into the differential equation, which means that it is a valid solution. So now you can see that we have come up with this exponentially function that is decaying in time directly from the error function itself. And what we do is, when we plot it by scaling the time and distances, we will see that with increasing time the composition profile clearly shows a decaying trend, and also the solute is spreading out into the domain away from the 0, which means that the physical behavior of the composition profile is quite logical as we expected. So this is a solution that we have readily at hand, and we also see that this solution guarantees that the total composition in the domain is fixed as given by the boundary condition where we started off. And as you can also see, the profiles are quite smooth, which means that it is not to be used for t is equal to 0. In fact, if you substitute t is equal to 0, the composition profile would blow up, and that's not the reality. So we will not apply this solution for t is equal to 0. For any finite time it can be applied. The third and the last solution for the transient diffusion equation is a very general kind of a solution which is applicable for a number of scenarios, and that's basically the sum of a series. And the problem definition which we have in mind, why we take up this particular solution case, is as follows. During homogenization of a segregated alloy, maybe because it is additively printed or it is solidified, and therefore between the dendrite arms there is a segregation, or because of any other process you have some segregation profile in the alloy, and normally we undergo heat treatment to ensure that this particular segregation is flattened out. And so we have a scenario where the initial and boundary conditions are very general, so they're not elegant and simple as we have in other cases. So we also realize from our preliminary mathematics that we have done earlier that any random composition profile can be expressed as a sum of sine and cosine functions, which means that by looking at whether a summation of sine functions could be used as a solution for the diffusion equation, we are actually trying to find a solution here. So the domain is imagined in this manner. The composition profile is important. We are interested in the kinetics of the decay of that profile, and we want to see how long it takes for it to be flattened out. And very often we are interested in this because the time and the temperature of homogenization is of very high importance for the industry. Too high a temperature may mean oxidation problems, and too low a temperature also may mean too much of time taken for the process. So there are certain optimal conditions that we want to look at, and the composition due to segregation is looking like this, which you can imagine could be as some kind of a sinusoidal variation. Now the scheme of finding out the solution for this particular case is that we take what is called the separation of variables technique. So we assume that the composition profile can be written as a product of two functions which are having only one variable. So we assume that the final solution of composition C is written as P times Q, where P is a function of X only and Q is a function of time only, which means that when we substitute that into the differential equation, we can inspect how the terms would look like. So the left hand term dou C by dou T would give you P of X into dou Q by dou T, and on the right hand side dou C by dou X will give you Q of T into dou P by dou X, and dou square C by dou X square is equal to Q of T into dou square P by dou X square. And when we substitute these into the differential equation, we get this form where we see that by rearranging on the left hand side you have got the terms of only Q and time, and the right hand side we have got terms of only P and X, and there is a D there because it's there in the differential equation. And because we know that P is actually a function of only X and Q is a function of only T, these two terms cannot have either X or T in them. It should be only a constant. Okay, and that constant we choose it to be minus lambda square. The choice of this constant is with some hindsight, because we realize that there is a second order differentiation of P coming up with X, and there is a sine function. When we differentiate it twice, then we have a minus sign coming. So remembering that, we actually have chosen it to be minus lambda square. So we substitute that and write the terms separately. So the left hand side is written as one equation where we can see that perhaps Q of T can be an exponential function, because we see that dou Q by dou T is basically proportional to Q itself. Similarly, dou square P by dou X square is proportional to P, but with a minus sign, and which means that it can also be a sine function. So we go ahead and try to find the generalized solutions. The solution for Q, as we have just mentioned, would be basically that Q is an exponential function, and in the exponent you must have minus lambda square D coming in. So which means that it is Q of T is equal to Q naught into e raised power of minus lambda square dt. So that's a solution for the Q function. Q naught is basically any constant for integration. Similarly, for the P, we have a general solution. Dou square P by dou X square is equal to minus lambda square into P of X, which means that when we think of sine functions are possible, then lambda can be inside the sine argument. So sine of lambda x is one term that is possible. You also can think of cos of lambda x. So because both of them actually can satisfy, a very general form of the solution would look like that: P of x is equal to a sin lambda x plus b cos lambda x. And so we have to substitute both of these into the solution, and so we plug them into the C, and then we got the solution as follows. We have absorbed q naught into a and b constants and converted them as a prime and b prime, so that the composition now is available as a general expression: a prime sin lambda x plus b prime cos lambda x into e raised to the power of minus lambda square dt. Now we have not mentioned what value lambda should be. Lambda could actually be any value, and this would be still a solution, which means that we can actually vary lambda and take the summation of all those terms, and that would also be a solution. So the most general form would then be a summation of these terms for the different values of lambda. So that's what we write as a general solution, and we choose those different values of lambda as lambda n, and we take the summation for n going from 1 to infinity. Okay, and we now see that there is a sine and cos functions with lambda, so perhaps we can replace lambda with 2 pi by L, and the n can actually be the factor of multiplication there, so that it looks more logical with the dimensions of x and L both being length. And similarly, in the exponential function also we can choose the tau to have the relaxation time scale tau defined as L square by 4 pi square n square d, so that our solution is looking a little more elegant, where very clearly L is the wavelength and n is a mode, and an and bn are the amplitudes of the sine and cosine functions, and tau is the relaxation time, and then we now have a generalized solution for the composition variation which satisfies the differential equation. And here we have chosen the colors in such a way that we can actually distinguish the terms. So the solution that we have sought is basically the C of x of t. C naught is actually the final average composition after the homogenization is complete, because when the homogenization is complete, t is actually almost infinity, which means whatever is multiplied with that e raised to the power of minus t by tau should basically be going to 0, which means that C naught is the remaining one, which means that's a final average composition after the homogenization is completed. Now what is in the green color? It is basically a summation of terms, which is basically the initial composition profile expressed using the Fourier series. So we readily can plug in, if we knew the initial composition profile in here, and then we have the solution coming up. And then the last term, e raised to the power of minus t by tau, is basically telling you how each of these waves, sine and cos waves with the different modes of n and wavelength L, are decaying with time. Okay, so that tells us basically how the homogenization process is taking place. Now we just take one simple example to illustrate this last solution. So the initial composition profile, we take it as just one term, and we write it as C of x comma 0, which means it is for the time is equal to 0, as C naught plus delta C cos 2 pi x by L, and the delta C is basically the amplitude of the composition variation. And we then can write the solution directly from what we have seen now, that C of x comma t is basically C naught plus delta C cos 2 pi x by L into e raised to the power of minus t by tau, which means that we readily have the solution now. And here the tau is basically given as L square by 4 pi square d, as we have discussed earlier. So this particular profile with increasing time, how does it look? So this is how it would look like. So the blue curve is the initial composition profile, which has the ups and downs, and as the time is progressing, you would see that after twice the relaxation time, the black curve is telling you how the composition profile has decayed. So it has come a long way from this value to this value because of the decay in this term. Okay, and that is actually the homogenization process acting, and through this we can actually now estimate the time taken, because the time scale is now well defined for us. Now as you can plug in, you would actually notice that when you take roughly about 4.6 tau as the time, then the amplitude will come down by a factor of 100. Which is quite good for us to assume that the homogenization is complete. So you could actually choose your error bar appropriately and estimate. And this is a very general solution and doesn't restrict on the initial condition. Initial condition can be any random profile that can be expressed as a summation of cosine or sine functions. So here are the references that we have used for this particular lesson. The first two references are already familiar to you. The Schumann's classical textbook on diffusion in solids and David Wilkinson's book on mass transport in solids and fluids. These are having very useful information about mass transfer with respect to the diffusion. And the third reference by Crank is actually like a handbook where practically every geometry and initial and boundary conditions that you could imagine, the solutions for the diffusion problem are made available. So if you are actually encountering an interesting set of boundary conditions before you attempt to solve, have a look at Crank's book. Most probably the solution is already available there. So with this we close the chapter on the transient diffusion in solid state.